Swayam Prabha. Digital India. Educated India.
In the last lecture, we discussed about the variation of the current in smooth direct current supply for the electromagnet and pulse direct current supply to the electromagnet. And we found that before really the current reaches to the 0 value, the on time or on pulse started and it never attained the 0 value. Then we also measure the forces with the help of the dynamometer, and we found that during pulse DC power supply there was a substantial increase in the normal forces that are acting on the workpiece compared to the smooth DC power supply. As you can see in this particular figure, that with the 0.08, that is lowest duty cycle that we could use in our pulse generator, the highest normal force that we are able to achieve is around 3000 Newton, while in case of smooth DC power supply it is around 70 to 75 Newton. So, there is a very large increase in the forces, normal forces, and this normal force is responsible for the penetration of the abrasive particle inside the workpiece surface. So, if penetration is very large, then what will happen, that the cutting force may not be large enough to remove whole of the material in the form of the chip. So, there are other phenomena and there are other problems also. If the normal force is very large, penetration is very large, it may lead to the defect in the workpiece being finished. So, let us see what are the problems we can expect. If you see here, this figure shows you the lathe obtained by static flexible magnetic abrasive brush, that is when you are using smooth DC power supply. And if you see on the left side, this is the figure which shows the smoother finished surface obtained by the pulse DC power supply. Here the duty cycle is 0.40 as you can see here, but still some grinding lay or marks are left over here which you can clearly see. When we used a smaller duty cycle, that is 0.08, we got a better surface roughness value and better texture of the surface. There were no grinding marks, as you can clearly see over here. The marks are only that made by the magnetic abrasive finishing process, and the time taken in case of pulsating flexible magnetic abrasive brush is much lower than the time taken by static flexible magnetic abrasive brush. But as I mentioned a minute back, that force is very large in case of very low duty cycle, and due to the very large normal force, the penetration of the abrasive particle is very deep, and as a result of that it may result sometime the defect in the finished surface. As you can clearly see here, that pit has been formed, and this pit has been formed because of very deep penetration of abrasive particle due to very large normal force acting on the workpiece through the abrasive particles. So, these kind of the defects are not acceptable on the finished component. Other kind of the defect, if you see on the right side, the workpiece, finished workpiece has a very micro nano crack, as you can see over here through the arrow shown over here, that some micro nano crack has been formed on the finished workpiece, although the surface roughness value is very good, but these kind of the defects may lead to the rejection of the finished component. If you perform the finishing operation at higher duty cycle, just like say 0.16 as the duty cycle, then those kind of defects are not visible on the finished component. If you go still higher, the surface roughness value may slightly increase, but those defects may be overcome, as you can see when it is performed at 0.24 as the duty cycle. So, the gap in these machine finishing processes was maintained as 1.5 millimeter and revolution per minute was 200 and finishing time was 15 minutes. Second issue which is important in case of magnetic abrasive finishing is, with increase in number of finishing cycles, surface roughness value RA keeps decreasing and attains an asymptotic nature. The question arises, and as a layman or in general way, if you keep increasing finishing time, its RA value should keep decreasing, but after a certain number of finishing cycles, its RA value becomes more or less unchangeable or constant, or it attains an asymptotic nature, and that surface roughness value is named as critical surface finish that you can obtain for the given finishing conditions and the workpiece. As you can see here, that based on micro machining conditions, critical surface roughness value keeps repeating. Now, here also this is the simulated one and these are the experimental ones. Now, what will happen that they are more or less constant or no change is there, but still slight variation you will find when you observe these values, because unless you have a highly homogeneous flexible magnetic abrasive brush, you will not get exactly the same value. So, slight variation is there, but this becomes more or less a constant value, and that surface roughness value is known as critical surface roughness value. So, some variation in the roughness value will be there, because magnetic abrasive particles mixture carries a range of abrasive particle size also. Now, suppose there is a certain mesh size whose diameter of the abrasive particles should be 2 micron, but this will not be, all the particles will not have the same 2 micron as the diameter, rather it will be varying in a certain range, and because of that variation in a certain range, there you find that there is a variation in the critical surface roughness value that you are achieving for the given finishing conditions. Now, how the mechanism is working? Let us try to understand this. As we have seen that you have the abrasive particles and ferromagnetic particles in the case when you are not using the sintered ferromagnetic abrasive particles, how it is working. So, you can see here that this is the abrasive particle and these are the ferromagnetic particles, and these ferromagnetic particles will align along the magnetic lines of force and they will form a chain, or they will form the chains. Now, in between the chains abrasive particles is entangled over here, as you can see here, and when this whole set of abrasive particles and ferromagnetic particles comes and strikes the workpiece surface peaks over here, then if the cutting force is more than the resistance offered by the workpiece surface, then it will shear off this peak, as you can see here in the form of the micro or nano chip, depending upon what is the normal force value, and this chip microchip gets separated out as the whole chain of the ferromagnetic particles and abrasive particles keeps moving in the axial direction, so, or tangential direction rather. So, you get the material removed in the form of the micro nano chips. Actually, in this way it works, and stages in material removal from individual irregularities, in three stages we have tried to explain this mechanism. Now, let us see the same thing, but in a different way stages in material removal from the surface. As you can see, this is the abrasive particle which you can simulate with this particular abrasive particle, and there are certain abrasive particles whose diameter is smaller than the width of the valleys. So, what it will happen that some of them will get sit over there, which are unless they move they will not be able to remove the material, but this is the bigger size particle. So, as the axial force is acting in this particular direction, it will move and remove the peaks, and it will shear off those peaks, and you will get this kind of the situation by the time it reaches to the end of the workpiece. Now, if you again there will be another abrasive particle coming behind this, and that also will keep shearing of the peaks, and finally, you will get this kind of the surface. Now, after this you attain this particular surface, what will happen that peaks have been reduced to the extent that their depth of penetration of the abrasive particle is larger than the depth of these peaks and valleys. As a result of that, as this process continues, and that fixed RA value of the finished surface is known as critical surface roughness value. Now, I also mentioned in the earlier slide that the critical surface roughness value will keep slightly changing from cycle to cycle, because the size of the abrasive particles is not constant. Unless that size is constant, this RA critical value will keep on changing. As you can see in the last figure over here, that there are the abrasive particles of different sizes, and they will create the scratches, or the depth of penetration will be different in each case depending upon what is the force acting on the individual abrasive particles. That is why that critical surface roughness value keeps slightly changing on either side of that particular RA value. This model is applicable to magnetic abrasive finishing, abrasive flow finishing, and magnetorheological abrasive flow finishing also, because all the three are working more or less on the same principle. Third issue related to magnetic abrasive finishing, which is applicable to other of processes which I just mentioned, like abrasive flow finishing and magnetorheological abrasive flow finishing, are rotation of the abrasive particle. With increase in current to the electromagnet or magnetic flux density, percent change in RA value keeps increasing. It attains an optimum value and then starts decreasing, that we have seen already one figure related to this. Now, what will happen if normal magnetic force Fmn is increased to a higher value? As I mentioned earlier, we have already seen the observations made during the magnetic pulsating magnetic magnetic abrasive finishing, that normal force increased to 3000 Newton from 70 to 75 Newton in case of a smooth DC power supply. So, with such a large value of normal force, definitely depth of penetration is going to be very large. So, when cutting force is not increased proportionately, what happens actually in MAF, that you are getting the cutting force from the electric motor and you are not changing the ratings or any other parameter, so that the cutting force also changes. Now, due to the very large depth of penetration, due to the high normal magnetic force, if cutting force does not increase proportionately, then the resistance offered by the workpiece material will be much higher than the cutting force being applied through the rotation of the flexible magnetic abrasive brush, and this rotation is attained through a electric motor. So, it depends on many factors such as medium strength, magnetic field, motor power, etc. Now, if this does not happen, that means cutting force does not increase proportionately, then what will happen to the abrasive particle? Two possibilities are there: either that abrasive particle remains implanted in the workpiece, or it changes its depth of penetration such that the cutting force becomes larger than the resistance being offered by the workpiece material, and this is exactly what happens during MAF. We have tried to show it through the observations, experimental observations on the finished component, as well as computation or application of finite element method. That we have already discussed, that this is the normal force which is coming due to the magnetic field, and this is the cutting force which is being applied due to the rotation of the flexible magnetic abrasive brush, and that power comes from the electric motor. These variation in the forces we have already seen. I have told you that during pulsating flexible magnetic abrasive brush, you get as high as 3000 Newton as the force, that is normal force acting on the workpiece surface, and you can clearly see there is hardly any increase or there is no increase as long as cutting force F c is concerned. That is very clear from this diagram also. Now, so three conditions exist over there, I will show you. Now, why rotation of abrasive particles in the brush or the medium takes place? If radial force is more than the required one, what will happen? Force required to remove material from the workpiece will be equal to tau s multiplied by A p, where tau s is shear strength of the workpiece material and A p is the projected area of the penetration. We have seen in the earlier slide that material is being removed in the form of the microchip. So, whatever is the penetration and that projected area A p of that particular abrasive particle and the workpiece common face area, that is known as A p, and tau s is the shear strength of the workpiece material. Now, if required force is equal to the cutting force or tangential force which is acting on the abrasive particle, then this condition is known as equilibrium condition. That means, neither cutting is taking place nor abrasive particle is moving, and it is just at the beginning of the moving. If required force is smaller than the cutting force that is acting on the abrasive particle, then what will happen? That abrasive particle will move further and it will remove the material in the form of the microchip or nanochip. If required force is greater than the force acting on the abrasive particle, then there will be no cutting condition. That means, abrasive particle will sit there inside the workpiece, and this is the condition which we are discussing about the rotation of this particular abrasive particle under this condition. Now, how rotation of abrasive particles in the brush or medium takes place? Let us understand this. The depth of penetration of cutting edge is adjusted by rotation of the magnetic abrasive particle. It is the case of the sintered magnetic abrasive particle. It can be just the abrasive particle in case of in case you are using the homogeneous mixture of the abrasive particles and ferromagnetic particles. So, until cutting force required becomes equal to the cutting force available or cutting force acting on the abrasive particle. So, that is the equilibrium condition, and this force can be calculated. What is the force needed under equilibrium condition? This is exactly what happens. Let us try to understand this. Now, this is the condition, as you can see here A p, and this condition is shown over here. Now, here the cutting force required is much larger than the cutting force F c or F t acting on the abrasive particle. So, what will happen, that this abrasive particle will try to rotate in such a fashion that in place of this H s is the depth of penetration, it comes lower and it becomes equal to H s dash. That means, it rotates and it attains the position like this, where H s dash is now the new depth of penetration, and if H s dash is the new depth of penetration which is smaller than the H s, then the axial force or the cutting force required will definitely be smaller to remove the material in the form of the chip, and this HS dash gets adjusted till the abrasive particle is capable to move the further. So, this is how it attains the condition when very large force is acting, normal force is acting, but still it rotates and attains the condition that it can remove the material in the form of the microchip. And whole of this analysis has been carried out using finite element method by Dr. S.C. Jaiswal of IIT Kanpur. Fourth issue is again an important issue. We have seen that while finishing cylindrical workpieces, there was a slot in the electromagnet, something like this. Suppose this is the pole, then there was a slot in the electromagnet, and say this is the north pole. Same way there was a slot, one slot in the side of the south pole. Now, the question arises, why these slots are there, and if we have one slot, why not to have 2 slots, 3 slots or 4 slots if a slot is advantageous. So, let us see, electromagnet has a slot along the its periphery y, and what is the optimum number of slots? We have tried to analyze it using finite element method, and some of the results are presented over here. You can see the magnet here, this is the magnet, and which is having this is a cylindrical magnet, and which is having the slot over here, and here is the south pole. Now, this slot has been made deliberately to take advantage of the slot in the magnetic abrasive finishing. This is how the abrasive particle is acting on the workpiece, and these are the magnetic lines of force along with these ferromagnetic abrasive particles are aligned, and this electromagnet rotates with the help of the electric motor. Now, while analyzing it with the help of the finite element method, we have made a particular domain, and we have assumed that along C2 del phi over del n is equal to 0 condition exists. Same way here also on the this is the center line of the magnet, where also again we have assumed del phi over del n is equal to 0, and this is the condition of the slot. All this has been analyzed, and we have found these results. Now, these are the slot in the magnet. Now, here if you see these results carefully, wherever there are the negative forces acting over here, and these negative forces are acting just under the slot. If you project it here, forces are negative. That simply means that just under the slot there is no machining. So, that area is known as no machining zone. But if you see other areas here, if you see this more or less horizontal line, this tells you the magnet without any slot, and the lines which are shown above this, that is having either one slot or 2 slots. So, we can see that in certain area the force acting on the workpiece is higher than the case when there is no slot. In certain areas the force acting on the workpiece is negative force, that means no machining is taking place. Now, because the work flexible magnetic abrasive brush is rotating, it is covering the whole area, and the workpiece is also moving in x and y direction. So, really speaking, this will not affect too much as the negative force are concerned, because at that particular time no machining will take place, but rest of the places the forces are higher than the case of no slot condition, and these forces are responsible for increasing the finishing rate, and that is why we found that with a slot in the magnet, finishing rate is higher compared to the case when there is a no slot. And also we can see there is a curve which is showing for 2 slots, and there is a curve for 1 slot. In 2 slots cases, the forces are slightly higher than the case of 1 slot, negative force as well as positive force. So, we also conclude that there is some advantage, but not substantial difference is there in case of 1 slot and 2 slot. So, at the most you can go for the 2 slots. If you increase 3 slots or 4 slots, you do not get any substantial advantage. So, at the most you can have 2 slots, but generally 1 slot only is used to enhance the performance of the magnetic abrasive finishing, and this is the highest force that you are otherwise also going to get at the edges of the electromagnet, and this contributes a lot as long as finishing is concerned. Now, you can see this particular figure where you can see surface roughness R A value obtained in a certain period of time, and that period of time without slot the R A value is higher and with slot the R A value is lower. So, that means it is giving better performance, or you can say indirectly that finishing rate is higher in case a magnet has a slot compared to the case when magnet has no slot. That is very clear from this curve, and let us try to see what is happening with TCMAF. Surface profilometer results are given here. This is the surface which was obtained before finishing, and this is the surface which is obtained after finishing, and you can clearly see that the before finishing the surface roughness value was 0.58 micron, and after finishing the surface roughness value came down to 0.19 micron. RQ is also there, that has also decreased, and RY also has decreased from 7.10 to 1.60 micrometer. So, there is substantial improvement in the surface finish or surface roughness value. Now, another case we started with the 0.51 micron as the initial surface roughness value, and in different cycles it came down to 0.11 micron as the final surface roughness value, which is substantial improvement by a factor of 4 after a certain number of cycle. However, the best surface roughness value obtained at IIT Kanpur for the given setup configuration was 40 nanometer. Now, there is another process, very versatile process for finishing purposes, because this magnetic abrasive finishing which we have seen in the last class and this class as well has big limitation that you cannot finish very nicely the components which are 3 dimensional in nature and which have complex configuration or geometry. In those cases this process is not very suitable. Let us see a new process that is known as abrasive flow finishing process. This work on this particular area was started by the Extrude Hone Company of USA. There are different models of this particular process, as you can see here. There are 3 types of the abrasive flow finishing process. One is one way flow abrasive flow finishing process, which is applicable for partially through cavity. Then there is two way flow abrasive flow machining process, it is for through cavity, and the third one is orbital abrasive flow machining process, which is for blind cavity. I will show you all the 3 types of the setup, and it will make you very clear that what are the limitations of all these 3 types of the finishing configurations. Now, this is the one way abrasive flow finishing process. Now, you can clearly see the workpiece is shown over here, and it has certain cavities, and this yellow color is the medium. Now, here if you see, this is the piston cylinder arrangement is there, piston is here, this piston is pushing the medium, and that medium moves like this, comes over here. This is the workpiece, and in the workpiece there are certain cavities, and through these cavities the medium is flowing. Now, this medium consists of viscoelastic material, abrasive particle, very fine abrasive particle, and some other additives just like mineral oil. Now, when this medium passes through these fine cavities, then abrasive particles come in contact with the peaks of these cavities, and as we have discussed earlier in case of the working principle of abrasive flow finishing, normal force acts over there, axial force also or cutting force also acts over there, and due to the penetration and cutting force it keeps shearing off the peaks of the workpiece surface and you get a better surface roughness value. And when this medium comes out, it is collected and again sent to the same passage where it is getting pushed, and this completes the circuit of the flow of the medium. And this way you are able to control the surface roughness value of these kind of the components. But mind it, here this is one way flow, flow direction is only in one way, and cavities are not the through cavities. Now, see, take this example, very interesting example. This is a cylindrical part which has hundreds of very fine holes, less than 1 millimeter diameter, and you can see this medium is coming out of this. Now, what is happening? Medium is being supplied from here through a proper tooling arrangement, and it is coming out of these holes and collected and then again resupplied from the top or from bottom also. So, what happens that when these abrasive particles come in contact with those peaks of the surface, they are sheared off and you get a much better surface finish in the miniature hole, and they are thousands or hundreds of number. You cannot finish by any other process except abrasive flow finishing or magnetorheological abrasive flow finishing process, because MAF also cannot be applied, because those are the solid particles and they cannot easily pass, and you cannot apply the forces the way it is possible with the nature of this type of medium. Then the second one, here is the two way, this is the two way flow abrasive flow finishing process. As I have mentioned earlier also, this is the workpiece and this is the upper cylinder and this is the piston and this is the medium, viscoelastic medium mixed with abrasive particle and additives. Now, when this medium is moving up and down, it comes in contact with the peaks on the workpiece surface and abrasive particles shear off the peaks of the workpiece surface and you get better surface finish. The best surface finish extrude hone equipments have obtained is around 50 nanometer. Now, this is the experimental setup which was developed at IIT Kanpur. Here you can see this is the hydraulic bottom cylinder, hydraulic upper cylinder, this is the medium upper cylinder and this is the medium bottom cylinder, and here is the workpiece and rest of the configuration is shown over here. Now, this is very good for the workpieces which have the through cavity like this shown over here. You can see these are the different dies and punches used for different applications, and these are the through dies. So, they are they can be finished easily by two way AFM configurations. But when you have the workpieces like this which have the blind cavities, how will you finish? You cannot use one way, you cannot use two way also. So, the extrude hone developed a orbital AFM process. In this process you see very interesting one, that you have the one cylinder and piston on the left side, another cylinder piston on the right side, and this is the medium and this is the workpiece. Just inverse image of the workpiece, here is the tool, and when this tool comes down, it comes in contact with the medium, it pushes downward and the medium comes in contact with the cavity of the workpiece which is quite irregular, and when this tool rotates, then medium also gets mixed up and it is medium is being pushed from here as well as here. So, that medium, there is a relative motion between the medium and the workpiece surface. As a result of that, those abrasive particles finish the blind cavity of the workpiece and you can get very good surface finish with this. Now, let us say the medium in abrasive flow finishing process or abrasive flow machining process. The medium in AFM process acts as a self deformable stone. How to finish different kind of the shapes which are shown in this particular slide is really a problem. Here you can see the octagonal hole shape which you cannot finish by normal finishing processes. Even with MAF you cannot apply that one here. This is the abrasive flow finishing process, where you have viscoelastic medium mixed with abrasive particles, viscoelastic material, additives, etc., that it will pass through very fine cavities or very fine features like this over here, and when this abrasive particle come in contact with the surface, then it shears off the peaks of the surface and it gives a very good surface finish. If there is a concave like this particular process can easily finish it. As you can see, the medium is going like this, it is moving like this, and it will be able to finish the cavities as well as plane surfaces or cylindrical surfaces. Then there can be the convex surface. This particular process can easily finish these convex surfaces, as the medium is going like this over the surface and like this, and abrasive particles are coming in contact with the convex surfaces, and they are going to shear off the peaks or irregularities of the convex surfaces. Now, here is very interesting example which I have shown. Now, in all these cases the working principle remain the same. As you can see here, here is the abrasive particle which is being pushed forward, say in this particular direction, and at that time two forces are acting. One is the normal force which is responsible for penetration of this abrasive particle into the workpiece, and there is the axial force which is moving this abrasive particle either in this direction or in this direction. Then this abrasive particle will remove the material in the form of the microchip. Now, since this is the flexible medium, it can go into the fine cavities and finish them, just like the holes we have seen earlier slide. Hundreds of holes can be finished in one go, and the diameter of the holes may be smaller than 1 millimeter. Here is another very complex shape. These are the cooling holes in the turbine blade. Nowadays, present day requirement of designers of the turbine blades is the turbulated cooling holes rather than the straight sided cooling holes like this, which were made earlier. So, the question arises how to finish these cooling holes, because if these cooling holes have very high surface finish, that is very low surface roughness value, then cooling will not be very effective. If they have very rough surface, then losses will be very high. So, the controlled surface roughness value of these cooling holes is required, and AFM or AFF is the only process which can give you controlled surface roughness value of such features. Now, these cooling holes in the superalloy have been made and fabricated at IIT Kanpur. As you can see, this is the actual photograph of the cut piece of the superalloy which is used for making the turbine blade. Now, the question arises, we have seen three different types of the configuration of the abrasive flow finishing process. Now, question arises, can we enhance the finishing rate using AFF process, because enhancement of the finishing rate means higher productivity, and this is always desirable by any industrialist. Let us see, people have been making lot of efforts for enhancement of the finishing rate using different configurations of the setup. Some of the researchers have used centrifugal force assisted abrasive flow finishing process, where AFF process was modified, and the central part in case of cylindrical workpieces they used a rod, and this rod could have different shapes as shown over here, and because of the rotation of this rod they assumed that centrifugal force is acting on the abrasive particle, and because of this centrifugal force the abrasive particle will penetrate deeper inside the workpiece, and if it penetrates deeper inside the workpiece and cutting force is large enough to remove that amount of material from the workpiece, then the finishing rate will definitely increase. Now, these are the 4 different shapes they have attempted with, and they claim that the finishing rate improved when they use these kind of the rods as compared to the case when there was no finishing rod. And they have gave some analysis also, and they have tried to prove that higher force is acting, and because of higher force penetration is also higher, and they did not give any analysis related to the cutting force. Other attempt was also made, where they have used spiral polishing method. In this particular spiral polishing method, as you can see that they have used a screw passing through the cylindrical workpiece, and this screw is rotated as you can see in this particular figure, and medium is flowing up and down as in earlier cases. As a result of that, the finishing rate improved to some extent. Definitely it is going to improve, because the area through which the medium is passing has decreased, and with the same force if you pass the medium through that restricted area, then definitely the radial force acting on the abrasive particle is going to be higher as compared to the case when there was a no screw. And because of this higher radial force, and if cutting force is large enough, then the finishing rate will definitely improve, and this is what they have found, that finishing rate has improved in case of spiral polishing medium method. And the situation when medium is passing through, this is the workpiece and this is the medium and this is the rotating screw, and definitely this becomes the restricted area. So, the larger radial force is acting on the abrasive particle, and that force is transferred to the workpiece for higher penetration. Then there was a drill bit guided abrasive flow finishing in place of screw. Some of the researchers have used the drill bit, and they rotated the drill bit, and same logic holds true here also, that this space available for the flow of the medium decreased, and because of the decreased area or volume of this space, the radial force that is going to act on the abrasive particles and getting transferred on the workpiece surface is higher than the case when there is no such drill bit. As a result of larger radial force, the penetration is larger, and if larger penetration is there, cutting force is large enough, then definitely finishing rate is going to improve. Now, they have tried to show it analytically that finishing rate will improve. They have analyzed it, and they have analyzed the motion of the abrasive particle in case when there is no drill bit, and this is spiral motion in case when there is a drill bit in the space within the cylindrical workpiece, and they have shown through experimental observation that the scratches formed or the material removed is not in axial direction, rather that it is also in radial direction. That is what is shown over here, that is S1 and S2, and they are making certain angle, that is the scratch direction they have shown over here. Then they have given the photographs in both the cases. Here you can see scratches are in this direction also, which are not in the axial direction rather than in the radial direction. And in AFF process, the movement of the abrasive particle is going to be in this particular direction, not in the inclined direction like this. And they have shown that in abrasive flow finishing process, the percent change in RA value is lower than drill bit guided abrasive flow finishing process for the same number of cycle. A experimental setup which has been developed at IIT Kanpur is shown over here. Various elements are shown over here. As you can see here, there is a hydraulic cylinder, lower medium cylinder, workpiece is there, hydraulic upper cylinder, upper medium cylinder, and then the workpiece is rotated with the help of a certain mechanism that has been fabricated at IIT Kanpur. And you can see, because of the rotation of the workpiece, the spiral motion is obtained for the abrasive particles with respect to the workpiece. workpiece, and because of that spiral motion, as I will show you in the following slides, you get higher finishing rate. This is the analysis, that is motion of active abrasive grain and finishing force in rotary AFF. This name has been given to this particular process because here workpiece is being rotated. Now, in case of normal AFF process, the abrasive particle is moving either in direction or in this direction, that is in the axial direction. Now, there is a certain length which is being covered by an abrasive particle when it is moving in the axial direction or normal AFF process, and when rotary motion is given to the workpiece, then in place of moving in the axial direction like this, the abrasive particle is moving in a spiral motion as shown over here. You can see that it is following the spiral motion. When it is following the spiral motion, then the total length of interaction between the abrasive particle and the workpiece increases substantially as compared to the normal AFM process. And if length of interaction of abrasive particle and workpiece increases, then number of the peaks that an abrasive particle is going to shear off will definitely increase substantial, and if that number of peaks sheared off in one single stroke is increased, then definitely the finishing rate is going to be higher. And second thing, since larger radial force is acting, so penetration also will be slightly larger. Now, here is shown over here what are the different kind of the forces that are acting. This is the radial force, this is the axial force, and this is the tangential force, and this is the resultant force that is acting over there in case of normal AFF process, and this is the force diagram for rotary AFF process. Various forces are shown over here, and it has been shown in different research papers that the performance of rotary AFF is better than the normal AFF process. Now, you can obtain the cutting force from F A square plus F T square under the root, and alpha, that is the angle at which this finishing force is acting, and this is given by V A over B T, tan inverse V A over B T, where F A is the axial force, F R is the radial force, F T is the tangential force, alpha is the semi cross hatch angle, and RAFF process, that is rotary abrasive flow finishing process. This shows you the motion of the abrasive particle along the periphery, inner periphery of the workpiece at different RPM. Now, you can see if it is 2 RPM, probably it will not be able to cover the whole surface of the workpiece. It will start from the one end and somewhere in between it will exit the workpiece surface. So, depending upon the RPM, how many rotations it is making within the workpiece surface before exiting from the other end, they are shown over here, and they have found that in case of rotary AFF process, honing kind of the scratches are obtained. As you can clearly see, it is in one direction and this is in another direction. So, you get micro scratch during active grain upward movement in this direction and micro scratch during active grain downward movement in this particular direction, and they are at a particular angle that he has mentioned as honing angle. You can clearly see the surface roughness, initial surface roughness with which the workpiece raw workpiece was taken was 900 micrometer, and final surface roughness on the component that they have obtained is around 7 nanometer. But this surface roughness value is obtained in a very small area. What is going to be the scenario in the whole surface which has been finished, and then one can take the average to find out the average final surface roughness value. Same way one can take average initial surface roughness value. as I mentioned that various mechanisms work in case of abrasive flow finishing of metals and alloys or non metals also, but in some cases when you are using the metal matrix composites, where you are using solid particles of abrasives in rest of the matrix material, in that case finishing mechanism are different from the mechanism that is followed in case of uniform metals or uniform material. Now, you can see here in this particular case that this is the metal matrix composite of aluminum alloy and silicon carbide abrasive particles. Fractured reinforcement is taking place over here when the abrasive of the medium acts on this, and this reinforcement particle is held very strongly. Then what will happen, that instead of being pulled out, it will get fractured as shown over there. Now, in this particular case valley due to the reinforcement pull out, if the reinforcement is projecting outward substantially, then the larger force will be acting on the reinforcement and it will be pulled out and it will form the cavity something like this. Now, surface peak due to the reinforcement pressure, and this is getting the shining one because abrasive particle has moved up and some material has been removed from it, and the same model same phenomena has been modeled as shown over here, that you get the microchip and here is the tangential force that is acting, and because of this radial force it penetrates, abrasive particle penetrates, and this is the reinforcement which is coming out, because the force acting or cutting force acting is large enough to remove the reinforcement from the matrix material. Abrasive attacking direction and reinforcement brittle fracture, you can see here abrasive is attacking in this particular direction and there is some fracture over here, and then this abrasive particle changes the direction because it is not able to pull out the whole of the abrasive. Same thing has been modeled over here. This is the fragment of the reinforcement and this is the abrasive particle in the medium, and this is the metal matrix composite. Surface peak after finishing due to firmly held reinforcement in matrix material, you can see here that this is the firmly held abrasive particle in the matrix material. So, slightly change the abrasive particle in the medium changes its direction, and without trying to pull it out, it moves, it changes its direction and goes away, and the same thing has been tried to show here in this particular model for explaining this particular phenomena. Thank you.